communicate with each other. That's pretty much what we've done for many years in Unreal Engine 3. And if you work with that older version of the engine, you will know that there were several tools that were kind of distributed in the sense that they communicated with each other. Swarm, for example, is one such tool that used network communication. And depending on who worked on the tool, we would be using some different kind of technology to transport the data from A to B. It could be UDP packets or TCP packets or an HTTP connection or a SQL Server database. We used .NET remoting and Windows Communication Foundation. Any technology, you name it, chances are that we've probably used it somewhere. And the problem with that is that it's a lot of stuff to maintain. There's not one single person in the building that really masters all these different technologies. It's a lot of code, a lot of duplication. As a programmer, I don't really want to think about how my data gets from one application to another. What I want to focus on in my application is to solve the problem at hand. How can I use the iPad to push some buttons and change the color in the configurator? I don't want to be worrying about things like network sockets and all these low-level details. And it's also difficult for the end user because they too need to become familiar to some extent with the technologies. If you're using network sockets, then you got to have some option screen where people can configure IP addresses and port numbers. It's all very cumbersome because many users don't even know what that means and what are the right values to put into that. So early on during Unreal Engine 4 development, I was trying to unify all these different solutions for writing distributed applications. And the solution for that is what I call the Unreal Message Bus. And one of the main goals was to have that system work just on its own. It just works. It's kind of like Apple Bonjour, for example. If you have an iPad on the network, the Apple software like iTunes, it will just find things and things just work. There's never anything that I have to configure. I don't have to enter IP addresses and port numbers and any of those technicalities. So I try to get that same kind of feeling. Provide the programmer with some mechanism to transport data from A to B without having to worry about how it gets there and without having the user to configure any specifics that are related to those transport details. So if you look at the slide here real quick, I'm trying to show what the message bus is. So it's really just a framework for exchanging data. A message in our system is really nothing else but a regular ustruct. If you've programmed in Unreal, you know ustructs very well. It's our way to mark up regular C++ structures, so they become a little more powerful. You can introspect them at runtime. They can be automatically serialized and deserialized and saved in packages and so on. So the message bus is able to send data inside ustructs from what is called an endpoint to like another endpoint. Endpoints are parts of code that are available to exchange data on the message bus. I briefly show here on the bottom how simple it is to declare a message type. And the code for sending and receiving messages is also pretty straightforward. First, you have to create an endpoint in your software. In the case of the McLaren demo, we had an endpoint on the iPad app and another endpoint on the configurator side. And this is a very simple use case in which the one endpoint is only sending data and the other endpoint is only receiving data. There was no bidirectional communication in this particular demo, although it would be very easy to do that as well. Now, messaging systems, if you're not familiar with that, They generally split into two separate paradigms. There's publish subscribe and request response. And the Unreal Message Bus supports both of those. The publish subscribe paradigm is a way to send a particular type of message to anybody who is subscribed to that particular type of message. That allows for exchanging data with other endpoints without knowing how to actually reach them. Like I said in the beginning, I wanted to make this really simple and things should just work. So the iPad companion app that we wrote, for example, it will, in regular intervals, publish a message and ask, hey, who is out there that can provide a service for remote controlling a virtual McLaren car? And then the configurator side will reply, I can. And there's some handshake where they will then, from then on, just communicate with each other. In particular, the companion app will just keep sending data to the configurator application. So that's one way of doing things. And the second paradigm, request response, allows you to send messages directly to a particular endpoint that you already know, because eventually you don't want to be publishing messages to the entire world. They would really be received and processed by anyone on the network. Once you found the configurator application that you want to interact with, you can then, from that point on, send messages directly to that receiver endpoint without having to publish the message to everybody. Now, everything I've mentioned so far about the message bus is like an in-process communication infrastructure, meaning that so far all the endpoints are located within the same Unreal Engine process. In our GDC demo, there were actually two processes. One was running on the iPad and one was running on a PC, two completely separate computers. So there is a messaging mechanism in the Unreal Message Bus called message bridges that allows for bridging two separate message buses in two separate processes or even computers over the network or some other transport mechanism. It could be UDP sockets or TCP sockets or HTTP. If you're familiar with existing message bus frameworks like RabbitMQ or Zero Message Queue, those could also be used as transport mechanisms. And you see that the code that we used to write over and over again to implement these low-level details is now hidden away in these transport mechanisms. Right now we only implemented one that's using UDP sockets. I hope to write some other ones in the future. And perhaps the community will help us well adding some more transport plugins. And once you have that, you can actually create really interesting things. It's not just for sending messages between two instances of the game, but you can also integrate this, for example, into a Maya or 3D Studio Max plugin. One thing that we really want to do is integrate the editor more with other third-party applications, so you can actually interact with them in real time. If I make some changes in Maya, I want to see those immediately in the editor without having to export my meshes and then re-import them in the editor. I'd like to be able to do all this in real time. That's another really cool application for the messaging system. And there's also a way to theoretically do this communication over the internet. There's some other system that I wrote, a message tunnel, which allows you to bridge the gap between different network subnets. The UDP transport itself right now, it uses multicast packets, so it can only see other endpoints that are located on the same physical network. But with a tunnel, you could extend this local network to anywhere on the internet. I can't think of any applications right now, but I'm sure some of you in the community will have some ideas for that. So where is this stuff being used, if at all? And it turns out the message bus is actually used in a number of systems already. If you go into the session frontend, for example, which is kind of the successor of what was Unreal Frontend in UE3, pretty much all of the features in here are driven by the message bus. Things like discovering your running game instances, like whenever you run some instance of the engine on your computer or elsewhere on the network, you will be able to see it in here, and you can interact with it. For example, here I currently have the Unreal console open, so you can actually send commands to it. Let's do show FPS, and if we go to the viewport, it should pop up. Didn't quite work as expected. So let me see. Did it go through?
Stats may not be enabled.
Oh, yeah. Well, you get the point. So here you can remotely interact with engine instances anywhere on the network. Same for the automation system. Whenever you run automation tests here, let's pick like a random one here. Let me see. Yeah, this one is fine. So here we use this automation system to run unit tests to verify that our code is correct. That automation system under the hood also uses the message bus to do the communication, because we're actually able to run automation remotely, which means you don't necessarily have to run these tests on your local PC, but you could actually execute them remotely on a PlayStation 4 or on an Xbox, where the same code might have completely different results. So it's important that we can do this over the network. One early, if not the very first use case for the messaging system was device discovery. Like whenever you go here to launch, we don't have any devices attached, but if you do have iPads and iPhones or Android devices or Xboxes or PS4s attached, there's going to be a list of devices here. And that discovery mechanism, like how does it find out about these devices? How does it know that they exist, and how does it deploy builds for them? That's also built on top of the messaging system. I just want to just briefly show the architecture for the target device management in particular. You don't have to understand all the details because it is somewhat complicated. But if you first look at the code, you will notice that there is an architecture that seems to be a little more complicated than it needs to be, perhaps. Usually, you might wonder, why doesn't the application talk to the device directly? If I have my iPhone or my iPad attached via USB to my computer, the editor could just talk to that device directly. Why does it need to go through these layers? You can see that here we split it up into the application layer on top, and then there's something called a device proxy, which is kind of like a remote representation of an actual device. There's a device service, which makes a target device available to an editor somewhere else. Then you have the actual target device itself, which represents like an actual Xbox or PlayStation 4. And then that code usually communicates with some platform SDK to send commands to the device or retrieve data from it. And then in some cases, like on iOS, we have even another layer, like the launch daemon, where it's possible to communicate with an iOS device, even if it's not connected directly to the computer, but perhaps just over the network on Wi-Fi. And when you think about all the different combinations, like all the different ways that devices can be attached or where they can be located, it it gets really quite complicated because in some cases you might want to deploy your game to an iPad that's connected to your local PC. In some cases, that same iPad might be connected to someone else's PC. Maybe you want to share the same device. If you develop for PlayStation 4, for example, you know those dev kits are really expensive. I think they're still almost $5,000. So you may not have the resources as an indie studio to buy a dev kit for everybody. You may just have one or two, and it would be nice to share that dev kit between multiple developers. We also have a use case where we want to run automation tests from our build system. So we haven't quite implemented this yet, but there will be a setup eventually where we run a farm of computers that have various mobile devices attached to it. There are so many different kinds of Android devices. We'd like to set up a farm of just Android tablets and Android phones in particular, and have our build system verify that everything is still okay. The code still runs and the content doesn't produce any errors. So there are many different ways that devices can be set up. And the cool thing about this architecture, what first looked somewhat more complicated than it maybe has to be, turns out to be a really simple solution, because we can model all these different use cases with the exact same code. Like if you look at these 4 silos here, which are just 4 examples of how the different layers can be spread out amongst different computers, you will see it's always the same thing: application, proxy, service, device, application, proxy, service, device. The communication in between is always the same as well. So we can use just one version of the code to support all these different use cases. Contrary to popular belief, I think the job of a programmer is not to write code, but to not write code.
Well, it's not my job to write code, so somebody needs to be there doing it.
Yeah, really, my most productive days are those where I delete a lot of code from the engine.
Mine too.
Yeah.
I just don't know what I'm deleting.
Oh, God.
Well, you shouldn't be deleting randomly, but every line of code that doesn't exist can't have bugs. It doesn't need to be read by anyone.
Wait, I need that on a shirt. Every line of code that doesn't exist can't have bugs.
Yeah,
that
it's
is
true.
Our
QA department's going to love that.
That is an
It doesn't need to be
line.
maintained. It's the less code you have, the better. So I really think if a programmer's main responsibility is to try and figure out how to not write code. It sounds a little counterintuitive, but that's really what it is. So with this setup, that's, as you can see here, it's mostly driven by the message bus. Under the hood, it really allows us to have just one implementation of the stack and use the same software stack for all these different use cases. Here's a little overview of how deployment works in UE4. It's you don't have to understand this.
That's good, because it's not gonna.
It looks very complicated,
and
but
it is.
The main takeaway here is that all these lines, they would usually happen all within the same process when the application talks to the device directly. In this case, with the layered architecture that we have, these arrows are possibly connecting different computers or different processes, but it's essentially the same thing.
In the case of something like lightmass or swarm,
right?
Doing distributed tasks or something like that.
Exactly. So let's take a look real quick. I think we still have a few minutes, huh?
Yeah, we're good on time. So yeah,
now,
if you want to do that.
You may be wondering, with messaging, a message-based architecture is highly asynchronous. You're not getting results right away. You're sending off a message. It could be a command, for example, do this. And then at some later point, the recipient will receive this message, process it, execute the command, and then perhaps it will send a response. There's some amount of time passing between all these steps, the sending, the processing, and the receiving. So this can be notoriously difficult to debug. you don't see right away what's happening like you would if everything were just function calls within the same process. So I wrote this tool called the messaging debugger, and it's still early on, which is the main reason I haven't talked about that much either. But you can activate it in the plugin settings. It's under messaging, and here's the messaging debugger. This is the second plugin down here, by the way, is the UDP transport. It's the only transport we have right now to bridge several processes. But if you enable the messaging debugger, which is turned off by default, then you can go into developer tools and fire it up. And you can actually start the tracing mechanism and see all the messages that are currently being routed within the process. In this case, the editor that we're in. And you see there are already quite a few messages going through here. Most of them are messages for locating target devices. You see there's like ping and pong. That's a very common pattern. If we run, for example, automation on our local instance here in the session front end, let me make this a little smaller. And by now it should already have, like when it populated the available automation tests. Let me pause this here for a moment. You see a bunch of messages going through to communicate which tests are available on this local instance. And let's just run one of these real quick. Let's run a couple of these and go.
Measuring in picoseconds?
These are microseconds.
Yeah, but the US?
I'm sorry?
You have milliseconds and microseconds?
Yeah, wow. There are milliseconds and microseconds. So you see a bunch of messages went through here to report the results. There weren't any errors in this case. There are some ways of filtering here. I still need to put a lot more work into this. This has been mostly one of my little pet peeves that I work on Epic Fridays. If you don't know what Epic Fridays are, it's like this one day of the month where we get to do whatever the hell we want.
I think you mean pet project. A pet peeve is something that drives you crazy. A pet project is something you work on the side.
That's right, a pet project.
Pet project, all right.
His pet peeve is that it's not done.
Yeah, that's it. Okay.
Yeah, it's not quite done. So perhaps later this year I'll have some more time to add some more cool stuff here, like breakpoints and so on.
Yeah, is any of this going to be included experimentally in upcoming builds?
Yeah, like I said, this is already available.
Oh, okay. So
it has been in the engine for several years now.
You just have to turn on the...
Yeah, you
just have to show it, and okay.
That's right. Messaging is always enabled, at least the in-process messaging, if you want to use it across processes. Currently, we require a command line switch. It's like dash messaging on the command line for game builds. It's just a safety restriction because we still have some instabilities in there, and I don't want to enable it just yet for everybody. It might crash, or it might cause security. It might have security concerns. So once you turn it on, you'll have that, and you can see this tool as well. I'll try to write up some tutorial, some documentation in the near future, and then I can talk about this in a little more
sure
detail.
That would be well appreciated.
Yeah. All right, so let's go back to the original use case for the GDC demo. So essentially what we do is we use the messaging system to continuously send messages from the iPad app over to the configurator. And they discover each other automatically through the publish subscribe pattern. So things just work. There's no configuration required. You don't have to enter IP addresses or anything. That example is super simple. We in fact only have a single message type, even though we perform only one action, like change the color or open the door or explode the car. we have just a single message that contains all these possibilities, and there's like an enumeration switch. So in a typical use case, you would have many different types of messages that communicate different things. We just tried to get this up and running quickly and just jammed everything into a single message. And another thing that we did, and this was somewhat overkill for the GDC demo, but it was an opportunity for me to try and test another system that I've been working on the side, which is an IPC layer built on top of the message bus. I said earlier that as a user, you don't want to deal with the details of network sockets. And as a programmer, you don't care about how things get from A to B. Well, it turns out that a lot of times that we use the messaging system, we implement the same patterns over and over again, like in that part. We're no longer dealing with sockets, but certain aspects like discovering some kind of service on the network and then starting to talk to it directly. That's kind of like always the same thing. The different use cases that I showed you that we have, they're all kind of built the same way. So again, I'm trying to simplify this code and reduce the amount of duplication, like these repetitive tasks that we have to do each time. So the reality is, while the messaging system is pretty cool, as an application developer, I don't want to deal with messages either. I don't want to deal with sockets, but I also don't want to deal with messages. Really, what I want to do is I want to execute some C++ function, and I expect it to execute it wherever it needs to execute, whether that is in the local process or in some computer remotely running over the internet or somewhere else in your office. But for me as an application developer, it's just a function call. So this is nothing new. People have done this for years in Java and in C#. .NET remoting is very popular. So I'm kind of trying to build the same thing for that. And for the GDC demo, I built something similar where maybe I can show it real quick. I think I have the file open somewhere here. So instead of sending messages, you see I'm really just making function calls on what is called an RPC client in our iPad application, and then on the configurator side, there's a corresponding RPC server.
Yeah, and then inside of the game mode itself, you can see the events that Max created, or the function calls are being read here, and then inside of that particular function call, I get the event, and then whatever data is being passed along as an argument, in this case, yaw and pitch for doing rotation.
Yep.
Wow.
And that's really all there is to it. So you see there's, here we're sending a tap, and here we're resetting the configurator. It's always the same message, fconfigurator command. We're just passing in different parameters, so it's kind of hacky, but it works just fine.
Yeah, it was flexible enough that Max was able to define it, Osmond was able to work with it, I was able to filter it, and we could get any of the multitude of configuration options, special events, and input controls to work off of that single message type.
Yeah, and then in the end, there's really a lot of code here. You can see there's some initialization where we create an endpoint to discover the configurator, and then the rest is just RPC calls that's using the message bus underneath. Similar on the configurator side, there are just blueprint functions to handle the messages that were received. So whenever, for example, there's an update in rotation, we just execute some delegate and blueprint.
Which is what I'm getting, and then whatever data that I'm being passed, I handle.
Yeah, and you may wonder, like, why do we have the same code and for the configurator side and the applications, the iPad app application side? It's actually all in the same module, and the reason is that I just put all this stuff into a plugin, and we could then compile the same plugin once for the configurator and once for the companion, and that's how we bridge the gap between the different engine versions. Yeah, and if you change it in one and it works in the other.
Yeah, I mean it was transparent enough that it was never an issue. the fact that the two were on completely different branches of the engine.
Yeah. So yeah, it's a cool way to write distributed software. People sometimes ask me when should I be using this, and for what should I be using this versus using other mechanism or writing my own. There's not really a general answer to that. I would say currently the message bus, it still has a lot of overhead. We're trying to make it faster so you can send literally tens of thousands of messages a frame without having any big noticeable impact on performance. That's not quite there yet. But if you can afford the overhead and you like the convenience, then you can definitely use the system. And I really hope that someone out there will start using it for integrating other software that's not Unreal. Maybe some 3D editing software or texture editing software or whatever. There's a lot of opportunity for integrating other things, also hardware devices and things like that.
Oh, well, speaking of things that people commonly ask you, I have quite a few questions.
Oh, no.
Yeah, I know. This is going to be pretty interesting.
Well, when we sit and talk for 50 minutes straight without letting people ask questions, they do queue up.
Yep. We got a few in here. So let's see. So at a base level, using this messaging system, you can convert multiple input devices or multiple devices to bridge inputs. I'm thinking like a phone's gyroscope manipulating input on a computer. And actually, there's quite a few questions in here about can I use this to control your VR app from an app on a tablet, or in general, I guess it's more of a can I use this more generically and to do things like with making your own custom controllers on it as an app, etc., stuff like that too.
Mm-hmm. Yeah, in principle, that's exactly what the system was designed for. And let me bring up the other slide real quick. Where is it at? Take a look. That was not it.
I think you were on it, but it was on a blank.
So if you look at this part here on the top right, where we integrate other types of processes that are maybe not necessarily Unreal Engine 4, that's really one of the big use cases that we wanted to support. The only limitation you're going to run into right now is that the only transport layer that we have currently implemented that will bridge the two processes is UDP socket based. So as long as you are using Unreal Engine 4 to write your application, which is possible, you can write standalone Slate apps using UE4. You will get all the things that you need out of the box, but we don't currently have an implementation outside of Unreal Engine that represents the other side. So you would have to write some, you would have to write the receiving side for your application in whatever language you're using there. It could be written in Python or in C# to basically translate the UDP network packets that you receive back into the messages that you're interested in your application. That's not super convenient, and I'm totally aware of that fact. Really, what I would like to do next is to write a transport based on HTTP, for example, where you can then just use any JavaScript or Python to exchange messages in JSON format. That would open up a lot more opportunities, because now we can also more easily support applications that are not written in Unreal Engine 4, but in other frameworks or programming languages or scripting languages too. Yeah.
All right. Well, then that makes a lot of sense then. I guess this one is probably going to be more for Alan, but they want to know, can you add different cars to this project, or is it all based around the one car?
One thing I did was, conceptually, I should have done this to begin with, was make a blueprint that handled all of the non-vehicle specific behavior, and then create a child of that to do
to like spawn in the vehicle.
Yeah, because instead of having the McLaren base blueprint be the one that's placed and everything is being done on, I should have done it with a kind of, parent blueprint
like
that,
a
that
showroom.
did all of the,
Yeah.
here's handling all the message input, here's setting up whatever behavior, and then the car specific, like what mesh and materials are applied to the car could have been done in a child. I didn't do that. There's no reason you couldn't do it that way. The one thing that you'd want to be careful with, and the reason I should have done it the other way, is the way I'm linking interaction points to the car and the navigator and all that stuff is by just casting it to the blueprint of type whatever and then setting that as a variable and then referring to that variable later. But because there's like 4 blueprints that all cast the car and then store the car, if I change that car blueprint to, like if I made a new blueprint and dropped it in, I can't just directly link them up without going through each blueprint and changing the cast.
It would break.
Whereas if I did it as a parent, I could then cast and get that it's the same class and things like that. So, yes, I could easily go into the existing car blueprint and change out the meshes, and there'd probably be a few things that would have to be fixed up to make sure that material assignments got called on the right parts and things like that. I didn't do anything that was specific to a McLaren in any way. There's just things that are specific to knowing that the mesh is this name, the material assignment is expected to be found in this location.
All right. Okay. That makes a lot of sense.
But yeah, I should have abstracted it one layer. It's the downside of having such a short deadline project. You do things to get it done.
Yeah. This was very much so built for the one demonstration.
Yes, but I really did. The reason that like the interaction points are kind of ignorant of what's going on is because I didn't know how many or where they were going to be. Yeah. So I built it in a very kind of generalized way. I could drop in as many or as few of them as wanted. I wanted to maintain that behavior throughout. Unfortunately, we didn't have the time.
It's a lot easier to just throw in some cast as opposed
to
creating a system of memorizing.
To do something where it's truly generalized, it takes a little longer in the front end because you have false starts. You have things that you realize I didn't consider when I was laying out the framework. So now I have to retrofit things in and make sure that they cascade down correctly to children and things like that.
That makes sense. Okay, cool. How did you import the CAD data for the car, or did you just like have a model sitting around that was in FBX already?
No, that was part of our communication with McLaren, was getting the CAD data to Francois and Min. Min did most of the importing. I don't remember off the top of my head the name of the tools that he brought in, but he brought it in as mesh data after doing some cleanup. CAD data tends to include a lot of additional polys that we wouldn't normally use in an in-engine model, right? For every pipe, it has the interior faces of the inner skin of the pipe and the exterior. So Min did a lot of cleanup work as well as UVing and material assignment as part of the kind of content massaging pipeline.
How many polys is it? Do you know?
It's around 15 million.
15 million polys.
Yeah.
Okay,
that's I believe that's combined with shadow generation though. So the shadow geometry as well as the base polys for the mesh. Given that the mesh isn't it's not a single mesh. It's a little harder to just look at it and go, oh, this
because
is
it's so
X
many
number.
parts that all
Exactly.
explode
It's
off. And
I don't know, something like 35, 40 individual chunks, and then there's sub pieces that are skeletal meshes.
Okay, I guess that kind of leads into the next question. Can you explain a little bit how you create a good frame rate using a high poly and detailed model like this?
So there's a couple different things. One is the engine actually renders triangles very efficiently. So having a scene like this where you have a lot of triangles is okay. It's minimizing the number of draw calls, so reducing the per chunk section count, right? Rather than having, oh look, this door panel has 25 different materials that happen to be like 5 materials that have the same body paint color, 5 materials that have the same rubber, condensing that down so that everything renders optimally. That, and there's careful tuning of the number of shadow casters in the scene, and how the scene is lit.
Right, that makes a lot of sense. Just to, I guess, yeah, because a lot of the shadow rendering is going to add a ton of extra weight.
Yeah,
so why
and there
not
were
just
things
render
like
the big things?
Daniel Wright was able to help out a little bit. Right, actually, he's actually going out of the country. And the last couple of days, he was able to spend some time doing the depth field ambient occlusion that gives a lot of the nice shadow geometry. Get back over to here. So, like, the fact that the car nicely shadows the tire underneath the arch of the car,
Yeah.
and also the interior shading. A lot of that is actually the depth of field, the distance field ambient occlusion
Oh wow.
that Daniel added.
Okay, so that's pretty impressive to, and so that's like the machine that we actually ended up rendering it on at GDC. Do you know anything about the hardware on that?
Well, we used the frag boxes.
Okay, so
So,
they're pretty powerful.
Yeah, we had 980s or Titans in most of them, I think. We were running it at 4K at GDC as well.
So,
I mean, obviously the frame rate was good at 4K. Running it in a more common desktop resolution is going to run just fine as well.
Yeah, and we have a Titan X in this machine. Not that we necessarily needed that for this resolution, but
yeah, there's actually like a lot of the material for the cars are pretty simple. Like there's very unlike something like game content where you tend to paint dirt masks and diffuse. There's a few high resolution textures, but really not much. It's for the car itself. Like the car paint has the texture mask for, or the
is that the wireframe of
Yes.
it?
Yeah, that's wireframe. Oh, come on.
That's nice. No,
What?
it's good. It's good. It's beautiful. You can make out every detail of the car.
Yeah, but there's only a texture for the metallic or the flake. There's no texture for the majority of the car. There's a lot of it is actual 3D geometry.
Oh wow.
Yeah.
That's kind of an impressive.
So, as a matter of fact, I think even some of the McLaren logo stuff, like that's 3D.
Oh.
Right. That's not.
Wow.
There's very little 2D stuff on the car, and what there is just for texture masking. Like there's actually pipes in here where there's 3D geometry for all those venting and the McLaren logo and all sorts of stuff.
Gosh.
Yeah. Wireframe in here is pretty nuts too.
Are we doing any custom occlusion calling for this?
Nope.
Oh, okay.
The engine's standard bounce-based metric occlusion.
Oh, okay.
So there is occlusion being done.
Yeah. It's just
one of the
kind
things that we were careful with was, or one of the things that Min had to be careful with was making sure that kind of part chunks, because we originally it's each individual part of the car, right? Every wiring harness, every pipe. Min collapsed a lot of those down into single blocks, but was tried to make sure that the bounds for individual blocks weren't too big. Like you didn't have a chunk of interior housing in the engine compartment, and then it also happened to have a plastic clip up in the front of the car, right? Because that would make the bounds the size of the car, and since we use the bounds to determine occlusion, it would almost never occlude. Yeah. So keeping the bounds for all of the chunks as tight as possible meant that if you're looking over here and this is behind the camera, it's probably not going to render. Or if you're looking at the front of the car and there's some big chunk that could potentially occlude, and you can see that if you open up the triangle count while you're actually in the demo, you can see that it changes as you move around the car. So there is some occlusion, but it's not, given the complexity and the number of pieces, there's not a ton of gains from occlusion.
Okay. Yeah, I guess when you're working with something that's already this complex
and dense, right?
Yeah,
it's just there's so many pieces, and they overlap and intersect, and all sorts of complexity there.
All right. Well, we're running out of time, but I'm gonna throw this last one at you here. What all from this demo is going to be available to the public specifically? Because I know that the car itself, the actual configurator isn't a public thing, but there are features and enhancements.
All the features and enhancements will make their way. I'm not sure what was in 4.11 and what's coming in 4.12. I think I'd have to ask. Like Zabir did a lot of the improved resolution for cube map captures. There's better crispness on the reflection lines and things like that. The distance field ambient occlusion. All the engine features will make their way down to release. This was all done kind of brute force right before GDC. So I imagine some of it will be in 4.12 if it's not already in 4.11.
Yeah, they were saying that it's not going to be in the first preview, and we're on to the second one. I'm not sure if it's into the second one, but there will be, as we go down, there will be more included from this into 4.12. So, yep, these features are going to be coming along. For the outro today, I'd like to say thank you both for coming along. We learned a lot. It was a really great stream. I'd like to remind everybody to join the May UE4 Jam. If you've got the time for it, it's going to be a lot of fun. Please go ahead and send me in your PM me your registration info. That's going to be a pretty exciting one. I'm still waiting to get more details on exactly what all the new stuff is coming.